Thanks a lot, ma'am. I hope I am audible and visible as well.
Yes.
Kindly permit me to share my slides.
Yes, you can share it. You are host now.
So I'll try to cover the topics given to me in 90 minutes. In case of need, I'll share my slides later so that we can discuss. My slides are not visible. Visible, ma'am?
Yes, ma'am. It is visible.
Okay. So for better visibility, I'm right now I'm stopping my video. Later on, I'll do it on it. So as ma'am is very kind giving me the topic that is of my interest. Many of my students are working in this area, and I'll try to cover the practical part as well in the Jupyter Notebook. So as this is I suppose this is the last day. Many of things have been done, but somehow I'll try to connect the previous things with this. First of all, this is means I would like to cover all these things, means 10 minutes each, but in case something left, I'll share the slides. So why sequence models in terms of NLP we are talking? So RNN is a recurrent neural network. LSTMGRUs are type of all the neural networks that process sequential data. But what we mean by sequential data is data is coming and we want the output to be generated in terms of machine translation, in terms of the image captioning, or in terms of any other thing, question answering. So many areas are there. Sometimes it's a sentiment analysis as well. So RNN is basically remember information from previous inputs, but may struggle with long-term dependency. So it's not like that the RNN is obsolete now, or only the LSTMs are working or GR is working. All our sequence models are working depending on the application. So we'll take some examples where this one is good and other one is good. So LSTMs and GRUs effectively store and access long-term dependency using a special type of memory that is known as a cell, and we have some gates. So why do we need it? The question is, why do we need to store the memory? Because we need to have the context of the sentence. That is very much important in the NLP. So what I am saying, how it is dependent on the previous sentence, that is what we want to store it, so that we get the concept. I have taken few examples where we need exactly, because every word, means many of the words have got more than one concept. So which concept we are talking about, that is to be stored from the previous story, right? So this is how this is starting of a sequential model. So I'll be taking one by one. First of all, everything starts when we started with neural network. It is an artificial neural network. How it is different from CNN. Although CNN we are not talking in this lecture, but somehow I'm trying to relate with the previous things so that we can comprehend. So in terms of properties, structure, layout, this is ANN is very simple. It is a forward feed neural network, and information flows from in one direction. While in CNN is a bit complicated, it has many convolutional layers. Of course, it has some advantage because it has a complexity. We have to have trade-offs. Sometimes we have some complexity, but it gives the results. Sometimes it's simple, but it's not at par we are expecting. So it is simple as it works on tabular and text data, while in case of CNN, it is generally used for the understanding image data. Image data is, as the input we are giving, it has a big, more pixels, let's say 1024 into 1024, the image. So it has lots of information. We need to extract it from the information. The ANN can work on a less data in comparison with the CNN, while the CNN needs more data that is to be trained. So in case of NN, it doesn't require any parameter sharing, while CNN needed. It doesn't understand spatial relation. That is what it is saying. The drawback we can consider in terms of images. Suppose in an image, there are many objects. They are placing from left to right or up top to bottom. But CNN can't help it in which order it's coming, the objects are coming. While CNN helps it in getting the, at what space it is presented, the object is presented. It cannot capture sequential information. So for example, how are you? So I'm fine. This is the answer. Then it doesn't take the sequential. It is for NNN. I'm fine and how are you? Both are same. Means the order doesn't matter. But in case of sequential, it can capture sequential information easily. So somehow. Okay. So this is the. Just give me a second. So looking at this diagram, we start from the general artificial neural network architecture. You can see we are providing input in terms of vector, and we can have as many as the hidden layers and ultimately output layers. In this example, we have got two outputs. They may be different. Looking at the another figure, it has a CNN architecture. Here you can see input is an array-like structure. And we have lots of convolution layers possible. And ultimately, they are fully connected and we are reaching to some output. Here, again, we can have different outputs. Similarly, sorry, I'm sharing it again, some issue. What happens?
Madam, any problem in?
Yeah, just a minute, ma'am. It's a technical glitch. I'm looking.
Just a minute.
I'm having two screens on my screen. Yes. Need to hide it. I'm not able to hide it. Okay. So what is the solution? Yes, better than. So sorry for that. So the difference between ANN, CNN, and RNN. So looking at the third picture of this slide, that we have RNN architecture is more or less similar to ANN, but we are giving the data in terms of vector. We have got many hidden layers as we have in ANN, but we are getting the output layer again is sent to the hidden layer. This is a change. So this is considered as a single node. This is considered as a single node. This is a single node. This one is a single node. So again, we are getting, this is the output, again is sent to the input. This is the difference between ANN and CNN. So what we mean by embedding? So in this presentation, I'll be using the term embeddings. Embeddings, what we mean by that, because we have our data in terms of either images or text that is to be converted in terms of the vectors, that is disease, right? So we have a big embedding, that is a document embedding, then sentence embedding, ultimately a character embedding or a word embedding. Word embedding is nothing but a it is used mainly in the deep learning, and this is the RNN, CNN, ANN, all are the part of deep learning. This is it is also known as a word vector. It is numeric, and ultimately machine understands only the numeric values. Those are some available vectors. They are pre-trained, per2back, or GLOB, and FastX. We'll be using all these in our NLP. Generally, we use it. So how CNN can be used in NLP? Is it not right that we cannot use CNN in a text or an NLP? We can use it very well, as we use CNN in images as well. So CNN is again a deep learning based approach that was originally invented for the image data, but we can use it for the text as well, right? CNN represents a feature function that is applied to constituting words or n-gram. What do you mean by n-gram? N-gram is very popular. That is unigram, bigram, trigram, and so many grams. So for extracting higher level of features, basically what we are trying to get, who are you, is an example of trigrams. So collectively, what do we mean by that? And if I say how, it is different. How are is different. How are you is different. So this is what we are trying to get in terms of grams. So first we have to take the embedding vector that is to be generated for the given text. This is our input. This is our input. We have to convert this into the embedding vector. So convolution filters are applied on this input embedding layer, which consists of applying a filter of all possible window sizes. Possible window sizes. This is one, and this is what window sizes, right? So the pooling operation is performed on these feature maps to generate abstract features. Ultimately, all the features are not very important. Some of them are important. Some of them are maybe redundant and having less value. So we need to generate the abstract features so that we can use it. In terms of NLP, mainly this is used for sentiment analysis, machine translation, question answering. Nowadays is the era of chatbots. So everywhere we are using this one. So looking at this example, we have, this is a sentence, a toy is joyously playing football with his friends in the park, right? This is a sentence. This is our input. This is what we have to convert into embedding dimensions. So we assume that this is pre-trained already and we can use any kind of model. And there are various filters. You can look at this. This is a pink, blue, and so many colors. So as many as filters are possible, we can take it. And using one filter, we are emphasizing on one of the important features. Similarly, the other feature, and ultimately, we are reaching to the pool of the features. And on the basis of something, some threshold, we can reach to the classes. Classes may be n number of classes, maybe binary class or depending. So here, looking at we have inputted the sentence and applied convolution layers. And the next step is pooling. We can have many pooling methods, maybe max pool or something else. And here we have some function on the basis of that. We choose which class is prominent, right? So there may be pre-trained. पहले से हमें पता है what are the y's, means we have this x is our input, and ultimately what are the different classes possible, because this is an example of classification. Those are already fixed. One of the class for one instance will be predicted, right? So next is a RNN. How RNN is different from CNN. So the difference between a CNN and RNN is the ability to process temporal information. Temporal is related with the time, right? We have, say, at this time, this is xt. So what is the information before that? That is xt minus 1. Or what will be xt plus 1. So this is nothing but time. At this moment, what is the value of this input and what is before that? That is temporal information is very much needed. So that is to be processed, and that happens with the use of RNN. R stands for recurrent neural network. RNNs are designed for this purpose, while CNN are incapable of effectively interpreting temporal information. That's why we have proceeded from CNN to RNN. So now the CNN is connected with the RNN. So we can see it using some examples that how RNN is useful. So RNA is again a type of ANN. Some modification has been made so that it remembers the previous data. So it is used to process the sequential data such as time series, speech signals, text, and this kind of a streaming data. It can handle sequences of varying lengths and can retain information from past elements in the sequence through the use of hidden states. Hidden states is it is an output of one state, one input, and it becomes output of this first one hidden state becomes the input for the next state. So this allows RNNs to model relationship between elements in the sequence, making them suited for language modeling. We have n-gram modeling, text classification, machine translation, and then we have sentiment analysis, so many things. Important example is, for example, I want to translate my sentence in Hindi and Hindi to English. Then this is a machine translation. We can have n number of translation machine languages possible. So looking at this, we have what X1, X2, X3, X4. This is the input, right? And we have this is hidden layer. Again, this is an hidden layer, hidden layer, hidden layer, and ultimately we are reaching to the output. So this is our output layer. So this is fully connected. All the inputs are connected with the intermediate nodes. We can use any input that is at that time that is known as a XT. And before that, it is XT minus 1. And we can reuse the same edge weights. That is the important thing. If we have to change the weights, or we can use the same edge weights. That depends on the application. So looking at this is RNN, right? Here, this is input in terms of vector, because we have already having the embeddings. And this is sent to this one, and looking at this arrow is coming back from this state. And ultimately, when work is finished, we are reaching to the output. So how do we unfold it? We have got many states. This is our input. Time of say time is equal to say 5 seconds, and this is time is equal to say 10 seconds or 15 seconds. Or somehow we can number them in terms of our clockwise. So this is our input. We are sending it to this. There are some weights. Those are assigned randomly initially. And doing some processing, we are reaching to output of this input. This is output of this input. Again, we apply something on this value that is coming out of this as a hidden state with some weights. Then weights may be same or may be different. It depends. So again, this hidden state with this weights sending back to this. This is a one node. This is one node. It is one node. We are treating this as a node 1, node 2, node 3. This is same. This one is same as this. We have this X is input. This is hidden state is coming back to this state. And this is as many as possible. We can do it. Ultimately, what we get hidden state and output. This is our input. This is our states. And this is our hidden states. And we are reaching to the output. So somehow we are making use of, at the time of XT, we are making use of the previous state that was XT minus 1. And its hidden state is HT minus 1. This is HT minus 1. So the question is, how many states do we need to store? We can use as many as possible, but somehow it's difficult to manage lots of states. So we can say this is very important, this is not important, this is important. So we can have some gates later, gates for remembering the things. It has the value, it doesn't have the value, it has a less value. So that's how we can have some attention or some weights so that we can reach ultimately to the output with the priority. It's kind of a weighted average. It's kind of a weighted average. We can have the weight that is not very important, say 0.1, and the weight 0.9 has got major importance. So how we can use RNN in NLP? So general CNN-based architecture uses n-gram or a window-based. N-gram means if I say trigram, right? तो मुझे 3 words at a time की value चाहिए, right? Bigram 2 ही चाहिए. So ये window बना सकते हैं इस तरह से, इस 2 ग्राम के हम window बना सकते हैं. RNNs, on the other hand, can learn the sequential structure of the data where every word is dependent on the previous word or one of the more words in the previous sentences. They do so by remembering previous information using hidden states and connect it to the current task. There are two things, there are two architectures in RNN. One is GRU and second is LSTM. These advanced RNNs can remember information for extended period. So how they are different? It has got 3 gates, it has got 2 gates. So it depends on the application. Either we want to use as gated or LSTM. The bidirectional LSTM is also possible. That is also very popular. It means from one side and other side as well, we can use the information. Why do we do it in terms of NLP? Because we need the concepts, context. For example, we have a concept of bank. Bank has got 2 concepts, for example. It has a river, means the edge of the river, or the financial institution. Which bank we are talking about? That we can get it from the previous data. Before we proceed, because we'll be using encoder and decoder in RNN. So I would like to have a look at encoder. Encoder is nothing but it is taking the input sequence and process it first and produces a fixed length vector representation that summarizes the information in the sequence. It's kind of a embedding we sent in terms of input, and it processes it and it gives the same similar kind of vector, right? Then RNN based encoder is an input sequence, one element at a time, and the hidden state out of this first वाला जो हमने xt भेजा उसका कुछ hidden state होगा, and the next is xt plus 1 that is to be checked. Considered. Ultimately, the final hidden state of RNN is then used and encoder's output, which is sent to the decoder. So encoder is again a big sequence, and decoder takes the encoder's output and generates an output sequence. It may be a machine translation or a question answering. How are you? This is a question. This is a sequence. My answer is I am fine. I am doing good. This is my answer. So this is what we send to the encoder. How are you? The answer will be I am fine. That is it is a job of the decoder. So an RNN-based decoder, the output sequence is generated one element at a time, and the decoder's hidden state is updated at each time step based on the previous output element. Let's take an example. Here, looking at the example, a woman is playing football. So we are sending this a woman is playing. This is input to the one node that is we say is RNN. Then the second one, xt plus 1 is sent to RNN. And similarly, we keep on sending, right, at the end of the input. And this is output of the encoder. It goes to the, in terms of a module, which is processed as an encoded vector. We can directly send it to this. We can connect it to this. This becomes the input of the decoder. So first one is this, इसके साथ connect है, ये इसके साथ connect है. इस तरह से decode होता है. Sometimes it happens that there's 2 words together and it has got only one output. That is also possible. Sometimes 3 makes it happen. Say I say cloud 9. Cloud 9 is taken as a one word. It's a phrasal kind of thing, right? Pin code. If I separate them, they make a different sense. So it is to be understood that this should go in this a woman की जगह हमें लिखना चाहिए a woman. So these kind of thing is also processed. So this is the function. We send this X as input, H is hidden state, and we get output as well as the hidden state. When we process hidden state, it becomes the function Y. It's not directly. We write a function which takes the previous hidden state and the input. It gives the hidden state as well as the output. There's a big difference between H dash, that is the current hidden state, and the Y's output. This is a function of R and N. So this, look at this. We have function f. This is our x1. At this moment, at this time, this is x1. Next time it will be x2. And this h0, if we don't have initially, we can assume it. We can give it a random, or we can start with 0. And we pass h0 and x1 to f. F is nothing but a function. It return backs the h1 that will be used in the next one. And we have got y. We have got y. Got it? So h1 is again sent to the next node. That is your f. And the new input, that is x2. What we'll get? We'll get h2, the next hidden state, and the y2, that is output. So h and h dash are the vectors of the same dimension. Because it's a matrix multiplication, we have to remember. We can multiply only m cross n and n cross 1. If this is a vector, then m cross 1 will be the size. So when we try, this h and h dash should be of same size. I hope it's clear. So similarly, we can proceed with this. We can have as many as input possible, like this. So no matter how long the input as well as the output sequences, we only need one function, f. The same functions. For example, if I have a function, f is nothing but x square. It may be x square, it will be x square for all. If f is different, if function is different, then it becomes feed-forward neural network. This may be treated as another compression from fully connected network that we have seen in CNN. So this is an advanced picture. If we have these two functions, f1, f1, f2, and here we have f2, f2, f2. So these are two functions. This is f1. F1 is getting x as an input. It initially is x1. While the another function f2 is taking z1 as input and g0, that is a hidden state, and giving us hidden state g1. So we start from this direction. Here we start from this direction. Here we start from this direction. To consider, it's not only that we need the previous story. We can reach to the end, and ultimately this story from this side also needed. So this is also combined in this case. This is also combined in this case. Ultimately, the output is our new function. Here we'll pass output of this one in terms of z, and output of this one in terms of y. And P3 is a hidden state. So how they are possible means, what is LSTM which makes use of these memories? So why we are not happy with the RNN, simple RNN, right? There are two issues. First is vanishing gradient problem, and second is long-term dependency issue. We are not happy with the RNN in terms of NLP because we need to remember the previous story and sometimes the upcoming story as well. So we have to make the combination of these two. So LSTM networks combat RNN's issue. What are the issues with the RNN? First thing is a vanishing or exploiting gradient problems. The second is long-term dependency. Long-term dependency issue. There are two issues with the RNN. That's why we have come to the LSTM or GRU, right? These are LSTM and GRUs are nothing but the type of RNN. But they remember the previous story as RNN has done it. But the case is RNN is facing two problems. First is vanishing or exploiting gradient problems. Second is long-term dependency. What we mean by vanishing? Vanishing is the slope. Gradient is a slope, right? It's like this. If we keep on this, I hope my pen is visible. This slope is diminishing, going down. So we cannot make anything out of it. It's exploding. या तो बढ़ जाता है या बहुत कम हो जाता है. So that is not desirable. We need to combat, we need to reduce the gap. Second is long-term dependency. It means it has a difficulty, RNN has a difficulty learning in long-term dependency because the gradients is kind of a slope. A slope means जब हम इधर से इधर जा रहे हैं, जब हम वापस इधर जा रहे हैं, because we have to tune the weights, we have to go back propagation, because what is input and what is expected here is a big difference. This is actual is say 0.9 and predicted is say 0.7. It's a big difference. So we have to tune the parameters, tune the weights, setting up the weights. We have started with some random weights, right? And ultimately हम यहाँ पहुँच गए 0.7 पे, जबकि हमें 0.9 चाहिए था, and it is not desirable. The difference is big. So we have to tune it again. So हम जब वापस उधर जाते हैं तो इतना ज्यादा चेंज करते करते we reach to some loss. जो ग्रेडियंट हमारा चेंज एक इपोक से दूसरे इपोक में जब हम चेंज कर रहे हैं तो पॉसिबल नहीं हो रहा है, राइट? तो ये जो दिस इज नोन एज अ ग्रेडियंट, इस ग्रेडियंट में या तो वो बहुत ज्यादा जीरो जा रहा है, डिप कर रहा है, या बहुत ज्यादा एक्सप्लोड कर रहा है. देयर आर टू इश्यूज विद द LSTM. सो मेमोरीज यहाँ पे हाउ डू वी कंट्रोल इट? सो देयर आर 3 गेट्स, दोस कंट्रोल इट, कि कितना कौन सी चीज पे हमें ज्यादा फोकस करना है और कौन सी चीज पे फोकस नहीं करना है. तो वी हैव, एज वी हैव सीन, वी हैव इनपुट गेट की गेट इज काइंड ऑफ जो हम और गेट एंड गेट करते हैं, वी कैन कंसिडर दिस एज अ गेट which determines which information from the input determines which information from the input gate. Input determines which information from the input should be stored in the memory cell. Memory cell मतलब जो कि याद रखेगा, उसमें हमें कितना रखना है, तो वो कैसे डिटरमिन होगा, वो इनपुट गेट बताएगा. और फॉरगेट गेट का मतलब क्या हुआ कि जिसे हमें बिल्कुल कम वैल्यू देना है, कम अटेंशन देना है, कम वेटेज देना है. हम उसको जीरो भी कर सकते हैं, कुछ वैल्यू भी दे सकते हैं. जैसे हमने बाकी रिग्रेशन वगैरह में पढ़ा, लासो और सारी टेक्निक्स, उसमें हम क्या करते हैं, जो भी अपने पैरामीटर्स होते हैं उन पे कितना वेट देना है, दैट वी रिमेंबर इट. सो इट शुड बी रिमूव्ड फ्रॉम द मेमोरी सेल. गेट कब यूज करते हैं, क्योंकि हमें मेमोरी में नहीं रखना है या बहुत ही कम रखना है. And ultimately we have the third gate, that is the output gate, which determines which information should be passed to the next. ये जो output gate है ना, वो हमें बताएगा कि हमें next gate में कितना रखना है. Got it? So if we compare till then, we have a typical ANN, general or standard one, and then what happens in RNN with this diagram. So these are the inputs, these are hidden layers, this is fully connected, and these are the outputs: input layer, hidden layer, and output layer. And here this is RNN में क्या हो रहा है, again input layer, hidden layer, and output layer. But looking at this, ये extra है यहाँ पे, ये देखेंगे आप, hidden से वापस H2 में आ रहा है. It was not there in the ANN. hidden से H2 से H3 में जा रहा है, ये भी हम, इसको भी हम यूज कर रहे हैं. अल्टीमेटली जो H0 है, इसके पास सारा आ गया. सीक्वेंस X1 को H1 मिला था और इसको शुरू में H0 मिला होगा, और H1 को हमने पास किया H2 को, H2 को पास किया H3 पे, H3 को पास किया H4 पे. Right? So this is an extra connection in RNN. Now look at this LSTM. We have this input layer, hidden layer, output layer is more or less same. We have what? Gates. H1 से यहाँ पे कितना जाना है, इस hidden से कितना जाना चाहिए, कितना forget करना है. That is to be checked. So in addition to this red line, we have a green line as well. Got it? So this is how we can see the clarity in three models. What's happening in RNN also, we are sending from hidden states to a next hidden state, but we are sending as it is. Well, in case of LSTM, we can send to some extent. हम कुछ भेज सकते हैं, कुछ छोड़ सकते हैं, कुछ रख सकते हैं. हमें सारा नहीं भेजना है. Got it? So next we have a GRU. GRU is the version of RNN. It has the different opinion. ये इसका जो कहना है वो कहता है कि रेड और ग्रीन के अलावा भी मेरे पास कुछ है. That will show it. So now come to the LSTM. LSTM में क्या होता है? Vanishing gradients. It was the problem. So vanishing gradients problem is a problem that is encountered during training neural networks by using gradient based methods like back propagation. Back propagation में क्या करते हैं हम? We want to tune the parameters such a way that जो हमारा law actual है और जो predicted है, they reach to the near, the similarity होनी चाहिए. अभी जो मैंने example ले रहा 0.7 and 0.9, they have a big difference. So it means what we have set up in terms of weights initially were not good. We have to tune it. तो हम कैसे जाएंगे? बैक से जाएंगे, फिर से आएंगे, फिर से बैक जाएंगे. अल्टीमेटली कब तक करेंगे? जब तक कि हमारा जो लॉस है that is bearable. Means if I say 0.9 is expected, I am reaching to 0.8999. That is okay. It depends on the application, what is needed. So in this, an RNN is unable to propagate useful gradient information from the output end of the model back to the layers near the input end of the model. This problem makes it hard to learn and tune the parameters of earlier layers in this one. Just because of this one, from RNN to LSTM, we reached this because we want something to be remembered and something to be forgotten. So if I summarize it, LSTM is a type of RNN designed to handle the problem of vanishing gradient in traditional RNN. What is this problem? This problem is tuning the parameters of earlier layers in the network. We are going back. So हम इतना चेंज करें थर्ड वाली लेयर से सेकंड वाली लेयर पे जब जा रहे हैं, तो ऐसा नहीं हो कि वैनिशिंग ग्रेडियंट हो जाए, वो जीरो डिप कर जाए या फिर एक्सप्लोड कर जाए. दैट इज
मैम one request, ma'am. Actually, participants are from different countries and different states, so they are unable to understand Hindi.
Sure. Understood, ma'am. Sorry, I'll take
yes, many comments we have received.
Yeah, sure. Sorry.
There are so many messages on chat, actually.
Okay, I didn't see it. I'll check. This makes LSTM well suited for tasks such as sequence-to-sequence modeling, speech recognition, and machine translation. These are the three important examples I'm taking it. Apart from that, question answering, and we can have chatbot. So LSTMs have been widely used in various NLP applications and have been shown to perform well on a wide range of tasks. It is being said that it is giving good results, but still we are not happy. We'll go again with another things. So what happens in the case of LSTM? How does it work? It has got 3 gates. Forget gate. So something doesn't have that importance. So we can keep the value weights lesser. Input gates, we have to remember it. We need it. And ultimately output gate, which gives the value output to the next hidden state, right? So let's take how does it work. So this is our input, xt minus 1, xt, and xt plus 1. This is, we have this is taken as a node. this is what we are using the lens to see what happens in the same. This A or this A and this A are the same. The working is same. So let's take a simple node. Here we have input xt. This is our sigmoid. We have here point-wise multiplication. Point-wise multiplication looking like this. So this is 1, 2, 3 value, and here 4. Hypothetically, I'm taking. So 1 is multiplied with 4, 2 is multiplied with 5, multiplied with 6. I hope my pen is visible. So this is point-wise. So if I have a weight that is 0.1, here I have a weight 0.01, and here something, anything, or here weight is 0, that is to be forgotten. The value is not to be remembered, and weight is 0. Whatever it has, and it is multiplied by 0 will be 0. It's a kind of forgot or forget. And if weight is 1, whatever we have here, that is to be multiplied with that will be remembered as it is. So this is how weights are from 0 to 1, right? How much weight we are doing, we are giving to the particular the input that is to be remembered. So this is our sigmoid, and this is our 10H. 10H is hyperbolic tangent. I'll let you know what we mean by that. And this is again sigma. We have got 3 gates over here. First is this, second is this, third is this. Let's take an example. This is point-wise operation. This is point-wise operation. This is vector transfer. Here we are transferring. This is concatenation. Concatenation is adding at the end, and this is copying the same thing to the next one. So these are the symbols in which in LSTM we are using it. So this is cell state. This is cell state. This line. This is cell state. This line. I hope my pen is visible. This line, the bigger line is going to the next state, is a cell state. So this is our cell state. Here we have X or cross. This is our multiplication. This is our concatenation. And from this state, cell state, we are reaching to this state. What's happening inside that? Let's take a look. So this is our forget gate. Computes from 0 to 1 values using a logistic sigmoid output function for input xt and the current hidden state. I hope you understand sigmoid. We have you have done the classes as well. So next is a multiplicatively combined with cell state forgetting information where the gate outputs something close to 0. If I say 0.0001 is something close to 0, it means we don't want to remember it, or we want to remember it for a with a very less weight. So this BF is nothing but a bias that we have to tune it in advance. Bias, the same we have seen in this one. Initially, for the sake of convenience, we take a 0. Bias, it means the difference. For example, this is actual and this is predicted. And this is bias we are adding so that we can reach to the equal thing. Initially, we can set something that is near to 0, and later, it depends. For the sake of simplicity, I have taken in my examples 0. So this is sigmoid, and what we are passing in the sigmoid is, this is weight of forget gate, F stands for forget gate. This is our hidden state, and this is our input state. So this weight is to be multiplied by the hidden state. These are nothing but the vectors actually. These are nothing but the vectors. So this is again a vector. Xt is a vector, this is vector, and somehow this is to be added. This bias is to be added. Here initially we are taking 0. And this value, whole value, is to be passed to the sigmoid function and reaching to the forget gate. So that's why F stands for forget. This is F stands for forget. This is first one. The second is, this is for the sake of convenience, 10H can be used as an alternative non-linear function because this is our linear function, but in real life it doesn't work. So somehow the non-linear is this, right? So this is this. So used to produce threshold output between -1 to 1. This is 10x function. It is -1 to +1. And these are the inputs, x. Anything from minus to plus. If I have a value 0, x is 0, 10h x is also 0. If I have a value 2, it has some value, this is some value in between 0.5 to 1. Here, right? And this is 1. This is 1. So what we mean by the next gate is input gate. We have seen forget gate first, this first one. The second is input. Second is input. This is input gate. Look at the input gate. So actually, you may say that some complexity has been increased in LSTM, but of course, it is needed to remember few of the things and to be forgotten few of the things. So this is input gate. So we need to input the entries in the cell state to update by computing 0, 1 sigmoid output, then determine what amount to add. What is to be added or subtracted, means forget. From these entries by computing a 10h output that ranges from value -1 to 1. This -1 to 1. Function of the input and hidden state. This is this. That's why we have taken 10h here. So this formula, this is input formula. Input, what we have done, we have some weights. Those to be multiplied by hidden value. Those we are receiving from the previous one. And xt is the input from this state. Right? This is xt. And here hidden is previous one, xt -1. And this is again bias of input. Initially, we can assign anything. Right? As we have done lots of examples of deep learning, we can choose as the weights randomly, and we can choose the bias. So it's means from my experience, I generally start with the bias or until unless it's given in the problem. The next gate is we are about to reach to output gate that is to be sent to the next hidden state. So we need to update the cell state. This line, this is a cell state. So we have done this one. This is forget gate, and this is our input gate. Right now, we are receiving the things from this line and this line. Got it? And this is to be plus, means addition or and we are reaching to CT. CT is the new state. Is FT into CT -1. And IT, this is our input gate, and CT -1. CT. It is reaching to the new gate, third gate. Hidden state is updated based on the filtered version of the cell state, scaled to -1 to 1 using 10h. That we have seen. Using 10h, why did we use 10h? Because we wanted to scale to this one. Because we have a non-linear function. So looking at this one, this is our OT. OT, how did we reach to OT? B0 we know, HT we have computed from the previous state, and this is our new latest XT, and we have passed this one, this data, this whole data to sigmoid, right? And sigmoid has got some values, like this, 0.9, 0.8, 0.6, right? Which has the highest priority? That is the output. And that output is again, this output is multiplied by this 10h CT. CT is this state, this one. And we have calculated from this one. So of course, there is a computation, mathematical computation, but it has some results in terms of forgetting and retaining. So we have done this one sigmoid with forget get. This is our input, and this is our output, and this is our CT. Got it? So here we have received this is cell state. Here we have again hidden state of previous state. This is third node. Yeah. Here we are getting the hidden state, and this is our new input. So this state is considering the new input as well as the previous value that is coming from the previous node. Right? So this is, again, we have to do it, keep on doing. Ultimately, we are reaching to the output. So what is the idea behind it? It is changed slowly with only minor linear interactions. This is more or less a linear interaction, but slowly we are doing, gradually we are reaching to the things, and very easy for information to flow along with the unchanged this. This is important thing. So this cell state is a combination of forget gate and the input gate. And basically, we can say this is the output gate. So LSTM has got 3 gates: input gate, forget gate, and the output gate. Output gate says how much information is to be sent to the next state. And the next state is getting input fresh and the previous information. Got it? So if I say my brother's name is Alex, he is 29 years old. He is 4 years younger to me. My age is this, my brother's name is this, he is 4 years younger to me. So somehow we have to remember the previous story, who is who, right? At the last, I'm saying, say his name is Vinay. At the last, I'm saying, what is the name of my brother, right? This is how we have to remember the things. And what is the age of my brother? My age is this, my brother's name is this, he's younger to me. So what we want this to be retained. But something that is not useful, for example, I am talking about the camera. Camera has got many features. So we have to retain, I'm worrying about the price of the camera, not the size, not the pixels, not the clarity, something. I'm worrying about the price. So I have to focus, I have to give the attention only on the price. Remaining things I have to forget. So I'll keep carrying the price things, right? Or some more than a price, as the size of the camera or the clarity of the camera, 3 cameras, 2 cameras, I'm talking about a mobile. Mobile has got how many cameras? 3 cameras. What is the price? What is the clarity? What is the RAM? What is the size, storage? So many things. So somehow we are reaching to the attention. What keeps us taking the attention? What features are attending? So in short, this I can show you again. This is our forget gate, means it has a lesser value, and input gate, it has a higher value. This is to be retained, this is to be forget. Sometimes we forget it at all, 0 weights, and sometimes we keep at some part. This is our output gate, controls what goes into the output. And here we are reaching Y sigmoid or 10S sigmoid 0, 1. This is a kind of a trigger. If we receive 0 or we receive 1. So trigger is something, if it's beyond this threshold, then go up. If it's beyond that, go out, down. So again, here the same thing. We have got this FT is the forget gate. Yeah, this is a FT. This is FT. This is a formula. For every gate, visualize, we can do the visualization of these gates, but they are ultimately converted into the mathematical formula. This is the formula for the forget gate, and this is the formula for the input gate. And you can see the difference. What's the difference? It's about the weights only, the change in the weights. If weights are higher, we need to remember. If weights are lower or lesser, we need to forget them, right? So somehow anything we are receiving, we can't take beyond the range. Somehow we have to limit it. Is it from 0 to 1? It's from -1 to 1. That we have to use this function. Here we are using 10H. So because in the output may be anything. So we have to limit within the domain. That's why we have to use these functions. Either we are using sigmoid or sometimes 10H or other things. After using this input gate and forget gate, this is to be updated for the next node. This is to be sent to the next node. It's a combination of forget gate and the input gate. Got it? And here, decide what part of the cell state to the output. This is our output. This is our cell state. This is our output. Output is coming using this formula and the hidden value from this formula. And this is coming from this one. So all are related, right? So LSTM has got 3 gates: forget, input, and output, using some type of combination. Ultimately, what we are getting? We are getting the hidden state, hidden value, and the input. Hidden is the previous one, and input is the current one. Using these 2 things with various combination, we are reaching to the output and the hidden state. So hidden is again sent to the next state and so on. So this is, I'm zooming it. So here I have done the calculation. If you see it, wait, I'm zooming it. I hope it's visible.
Yes, ma'am. To some, yes.
So I have some inputs. You can see it here. I have XT is 2 cross 0.6 and 0.5. Randomly, I've taken it. And this is, I assume that the hidden state I'm getting, it initially it is H0. You can take 0 as well, but I've taken it 0.5 and 0.3. So look at these values. And this is coming from the previous state. This is CT minus 1 is coming from previous state. And here, this formula, this is HT minus 1 and reaching to this. I'll give you the Jupyter notebook for this. I have taken some values, and ultimately, this is how it happens. This is how so much calculations are to be done, and ultimately, this we are reaching to this HT minus 1. It initially started with HT minus 1, that was 0.5 and 0.3, and this is HT is 0.39 and 0.29. So see the difference? Earlier it was this and this is. And this is our CT. CT we started with 0.1 and 0.1, randomly I took. And this is 0.67 and 0.46. So many formulas have been used. This is a point-wise multiplication here. This is point-wise multiplication. This is sigmoid is used. And if this value is greater than this, then we say this is this. And we keep on doing it. This next node, these calculation, and again these calculation, and this is our HT, 0.44, 0.40. So all the operations we have applied, sigmoid, 10H, and the multiplication, concatenation, addition, from this, that, we have done it. So basically what we wanted to have this value, right? So I have written the Python code for this and provided some values in terms of vector. You can take anything, and ultimately we can reach to this. So if we try to differentiate between RNN and LSTM, in RNN, there's nothing like gates, and what we get in terms of hidden state and input, it goes to 10H and it gives a hidden state that is for this state only, current state, and as output. While in case of LSTM, there are elaborated things, input gate, output gate, and forget gate. This is an addition. These are the additional things. This 10H, this is 10H same, and it's reaching to this one. So here we are manipulating such a way that what is redundant or not necessary to have less weight, and what is needed to remember have more weights. So how does it go? What is the information flow of LSTM? We start from this. This is our cell state. We have hidden state, assuming that I have it already for this current state xt. And this is our weights. I'll explain it. So these are the outputs of gates. This is output of forget gate. This is output of input gate. This is ultimate output Z, and this is output of Z, output gate. So looking at this, this is Zi, this one. Zi is nothing but weights in the input state. This is current state now, and the hidden state, just previous state. And what we do, we multiply these weights with this one as well as this one, and we pass it into sigmoid. This is the outcome. The next is a forget gate. This is again depends on the weights, how much weights we want to keep it. Same thing, xt, ht, and we multiply and send it to output of forget gate. And this is, here we have got wi, this is wf, and this is w0. Again, these are the weights, and same input and output. This is z0. And here we have got weights, xt, xt, and I hope it's clear. This controls the forget gate. This controls the input gate. This updates the information. This is the ultimate information is sent to the next one. This is the next version of this LSTM p-hole. We can leave it for maybe some difficult part. We can leave it now. Now, what applications we can use for LSTM? So first is there are two types of machine translation. Neural is a NMT, and second is SMT, statistical machine translation. This is example of neural. Looking at this, this sentence is given in English. That is to be translated in another language, say French. So here we have economic growth has showed down in recent years. This is our xt. This is our xt for the next node, xt. And the same way, just we have seen it. In this case, this is a word embedding. This is an embedding of economic. Here you can look at this. This is a dark one. It is a prominent value that is consisted in this one word embedding. The growth, this is feature, this is feature, this is feature, and same way we are doing it for the next level, and ultimately we can reach to the equivalent to this one. The is la, and similarly for the other words. So as we have discussed what happens in the case of encoder, this is encoder and this is decoder. It's a bit complex. We have to use word embeddings. Those are already available. It has a vocabulary which has got embeddings. those are to be used. And here looking at the red one, that is your output sequence of this. We started with this one, and ultimately this red one is given to the next one, that is the input for the decoder. This is the output of encoder and is sent to the input of the decoder. This is one of the example, one of the application of LSTM. So here we are remembering the sentence, the detail. It's not like that at the last years means it is to be converted. Somehow this years is related with the economic growth. So we are remembering what has been said so far. Got it? So it's not like that it's doing one by one. It has some connectivity with each other, intra-verse. So as already I have discussed what we mean by attention. Attention is just like a weight. This is a notion of memory, how much we have to do it. So this is known as an attention-based LSTM, attention-based neural network. So it gained from attending at a multiple inputs through time. In broad terms, attention is one component of a network's architecture and in charge of managing and quantifying the interdependence. So what is the relationship between the input and output? It depends on the general attention. There are two types of attention, general and self-attention. So this is the attention between input and output, that is a general attention, while the self-attention says how the inputs, how the words or text is related with each other within the input elements. Attention and self-attention models have been some of the most influential developments in the NLP. Got it? Sometimes we say that is what I needed. Sometimes it takes by default. It takes, it's a self-explanatory that it takes. So looking at this example, we have, you can consider this Hindi as a foreign language. We have input in English, a woman is playing football. This. So we are inputting the word by word. Next. This is a part of encoder. This is part of encoder here. And what we are receiving out of this is output of the encoder that becomes the input for the decoder. Got it? This is C1 is nothing but a context, in which context it has been said. So every word have some context. And sometimes a word may have many context. So which context we are talking about, that is to be chosen precisely. Then only there is a relation between all the concepts. So as we do in information retrieval, what happens in the case of information retrieval? We have some documents, those are indexed, and we send our query that is to be indexed in the same way the documents have been indexed. It means the concepts are to be matched. For example, if I say Java, my context or a concept is a programming language, while Java may have a different context. For example, if it is a Java coffee beans, Java island, Java motorcycle. So which concept we are talking about, those are to be connected together. I'm working on Java. I'm working on what? I'm working on Java. It means right now my context is, say, some island. Yeah, it's a coffee beans. So somehow coffee beans will be there in the other concepts. Got it? So a woman is playing football. Ultimately, using this concept that has been decoded. Somehow this decoding, this is equivalent to ek in Hindi. Woman is mahila, is her, and that the order of the words in the different foreign language is to be as per their grammar, as per their the rules. We say in Hindi is a subject, verb and object. While in Hindi it is a subject, in English it is a subject, verb and object. While in this Hindi it is a subject, object and then verb. So the way the language is to be written, that is to be checked again. It's not like that we do a woman, एक महिला प्ले कर रही हैं फुटबॉल, ऐसा नहीं. should be like, एक महिला football खेल रही है. It is like a foreign language for you. Got it? That is a part of LSTM. So how we can differentiate between general attention and self-attention? General attention is the ability of a network to attend to different parts of another sequence with the output. What actually we want? We want output. That is our prediction. That is a role of AI. So how do we connect our input and output? That is our attention. So using the encoder-decoder architecture, where the encoder takes the input and output of the encoder becomes the input for the decoder. It attends the encoded representation of the whole input when making predictions. While in case of self-attention, there is no output. How they are connected with each other? I am working on Java. So work and Java. So somehow what is being said before this sentence, that is to be taken care of in terms of self-attention. So ability of network to attend to different parts of the input sequence so as to generate better representation encoding, that is a self-attention. So basically in real life, self-attention is very much needed because nobody tells us that what is the output. That is to be checked what is the story behind this statement is being said. The same example I just taken, we have say word bank, and that has been used in a sentence. So let's take the concept of bank. It has got two aspects. One is financial institution and second is a river bank, right? So which bank we are talking? Is a river or a financial institution? So in order to distinguish among these two concepts, that is needed. If we provide the context from the sentence, if we take it from the previous sentence, then it is a self-attention. And somehow, if we know the label of this sentence is going to be a financial institution, then it is a general attention. It provides the context from the sentence, thus the representation encoding generator is different from both the case. Actually, this is what the difference is. So NLP is having two big issues. First is a concept. First is a concept because it keeps on changing, right? It keeps on considered from the previous sentence, right? And second is too dynamic. It's too dynamic. Even the context is changed after some time, right? For example, if I take virus. Virus is related with my computer program, computer, or something with related with the medical. Which virus I am talking about? That is to be understood. That is to be actually that is not hidden. We have to find the pattern in which pattern we are talking about. That is the job of the attention. So look at this. We have got the law, and we have some concepts here. Those are related with this one. So this is perfect. If we do the machine translation, the law is law, the will is will, never is never. So if one word is related with one concept is okay. If it's more than that, then we have to check it. So here, look at this. The law will never be perfect, but it's related with law. This is nothing but is related is said about the law. Got it? So this is known as the anaphora resolution as well. What has been, if I say Sachin is a good player, Sachin is a popular cricketer. He is a very nice person. Who is a very nice person? It means we are talking about the Sachin. I wanted to look at these two, but I think time doesn't permit. I have taken all these studies in terms of information retrieval and transfer learning. We can leave it behind. The next sequence model is a gated recurrent unit. So we have started with ANN, then we have seen CNN, then RNN, then LSTM. Still there's a scope of change. The scope of means there's a possibility of something better. It depends on the application. As the name says, gated. It means it again has gates, but lesser than before. So it's again a RNN. It uses gating mechanism to control and manage the flow of information between cells in the neural network. Being a gated RNN, if it can capture long-term dependency, that is what we wanted to have in LSTM. But how it is, GRU is different from LSTM. As we have seen in GRU, we have got 3 gates: input, forget, and output. While in case of this, the number of gates has been reduced. As you have seen the complexity, right? So many weights, so many inputs and hidden gates that is to be multiplied, that is to be concatenated, that is to be added, this and that. So the GRU tried to reduce the complexity using reducing the number of gates. So here only 2 gates are there: reset gate and update gate. So as a result, we need less parameters. Earlier we had more parameters. So sometimes we say it's comparable to LSTM, and sometimes we say lesser. So if we have less complexity and equivalent accuracy or performance is equivalent to something, means it's a good thing. So they are used to process sequential data in a deep learning. GRU can be used for machine translation, text classification, as we have seen in LSTM as well. The same way we can use it. So looking at this diagram, earlier we had got, if you remember, here we have got input, and then here we have got forget. This here it was forget, and then somehow it was input, and this one. So it's a bit different from that. It has got same element-wise operator, means if this is to be multiplied, this to be multiplied this to be multiplied this to be multiplied this. And then concatenation, that is addition. Concatenation, iske baad, afterwards we have to edit. So how does it work? It has got 2 gates. First is reset gate, second is update gate, which controls the flow of information in and out of the hidden state. This is what basically we want. We want hidden states, previous hidden states value, those to be used. A reset gate determines how much of the previous hidden state is forgotten. How much we want to remember, how much we want to forget it. So how much new input is added, right? The update gate determines how much of the previous hidden state is kept and how much the new input is added. So more or less, these 2 gates are working equivalent to 3 gates. The output of the GRU at each time step is hidden state, and which can be used as an input to the next time step or the final output of the network. So let's take an example. The same way I have taken some values hypothetically, and I worked on this. This is my input. This is my hidden state. I'll use this as a reset gate, and this is our update gate. Using these sigmoid functions and some point-wise multiplication, we reach to this one. And the next one, we send again xt. Xt will be having same. So it's 2 cross 1. Again, we have got some values, say 0.7 and 0.3, for example, right? And this is to be processed like this, as we have done here. Got it? So these are the weights. This is the weight, this is weight, this is weight. We have to be very careful that our matrix multiplication is possible with the size of the matrix, size of the vectors. So here we have got 3 equations. First is reset gate and update gate, and this is our new hidden gate. Ultimately, this is multiplication point-wise. In the previous diagram, while calculating the values using above equations, we have ignored the bias values. Here we have ignored. These are different values that we have to set it. So all of a sudden we can't reach to these values. We have to tune them. In this example, you can see that these are the gates, these are the weights we have taken it, assumed it. And these are the values of UR. This is UR, this is UZ, this is UZ, this is U, this one. These are the initially set it. So we have to keep on doing it. It's an iterative cycle. We say number of epochs. So ultimately, we can reach to the what we exactly want and what is being done, the actual versus prediction. This is the program I have written myself in Jupyter Notebook. I wanted to show you, but you can see it from there. We have used mainly the NumPy because that is enough. Lots of calculations are there. And this is randomly we have generated the values. No biasing, randomly generated weights, initial weights. This is how it works. And ultimately, this is the output. If you can see it from here, this is new hidden state. We started with input and one hidden state that was randomly generated. And you can look at this biases. These are 0 initially. I've taken zeros. This is 0, 0, 0. Right? If you wish, I can share the Jupyter Notebook that I have created for you. So we can conclude what we have seen so far, CNN versus RNN. CNNs are commonly used for image classification. So it's not like that the CNN is good for that or CNN is bad, not doing good against RNN or RNN is doing good against CNN. It's not like that. It depends on the purpose, what we want. Sometimes I have seen in my experiments, CNN is doing good for image, very good for image classification. In fact, when you go in detail, because this is a small class, shorter duration class, we have one more architecture that is RCNN. So you can say it's a trade-off in between these two. So CNN are computationally efficient because it has less complexity. It can learn complex patterns in images. While in case of RNN, it's used for text and speech. So generally we use it for NLP. The work by processing input sequence one element at a time. That is RXT. And maintaining a hidden state that summarizes the information. The hidden state is updated each time, next time, next time, next time. And we keep on receiving the inputs from the previous state in terms of hidden state and the current input. So why it's not good? RNN suffers from vanishing gradient problem, these two problems, or long dependency. So to combat this problem, there's a option of having some gates, right? Those are LSTM and GRU. So LSTM are again type of RNN designed to overcome the vanishing gradient. So what is the problem? They work by maintaining a memory cell that can store information for long periods of time. The memory cell is controlled by gates that regulate the flow of information into and out of the cell. What is coming and what is going to the next cell. So these are able to learn long-term dependencies. That's why this is a challenge with the NLP usually. This is a challenge with the NLP because it needs the things to be memorized from the history. So as you have seen the example of ChatGPT, if you keep on asking, it stores, right? ChatGPT. So gated recurrent unit, GRU is another type of RNN designed to address the vanishing. This also can handle this one. LSTM can also handle it. This can also handle it. It has got 3 gates. It has got 2 gates. The working is a bit different, but they are somehow, from my perspective, they are doing good in NLP. Both are doing good. So GRUs also have gates that regulate the flow of information, but they combine the input and forget gates into a single update gate. So GRUs have been shown to perform similar to LSTM in many tasks while requiring less computation resources, right? So actually we are worrying about the resources. We have to optimize the things. We are worrying about the time. We are worrying about the computation. We need less computation and accurate, good performance. So here we have number of gates are less. So of course, complexity is lesser and computations resources are lesser. But more or less, when we talk about the NLP, it means we need lots of data in terms of documents. We need GPUs to work such a way that they are computed in parallel.
I'm sorry to interrupt. Yeah, you are already at the end. Yeah, sorry to interrupt you.
So I have got some references at the last, and my email ID. The participants can note it down. They can write an email if in case of need.
So thank you so much, Professor Mittal, for this excellent session on this LSTM, which are, I mean, these things are very important for understanding and moving further. So I hope all of you have enjoyed it. And so whatever you have learned now in the lab session, you will be implementing.